if on that document, why might it be super helpful to be getting the section numbers? Why might that be on there potentially?
Maybe there's examples in that section about that topic.
Oh my goodness. That's crazy. What if there's a definition on that topic list and you're like, oh, I don't know where to find that definition in the textbook? What do you possibly might hypothesize?
Chat.
In theory. That it's in that section. So does everybody know how to access the news feed from D2L? Does everybody know how to click the button that says download the PDF with the... Okay, the reason I mentioned that is because when I really think about it, I really don't know what you guys know how to do because I simply haven't had the chance to really pull that. And so that's the function of today. So if you don't have your notes ready to go and answer some questions, at some point today you are going to be on a hot seat and you will have to answer something for the class. And I will not move on until you answer the question. Okay? So this is one of those things where it's like normally I ask something, dead silence, I point somebody out, dead silence, and then somebody else thinks that the silence is too painfully awkward, and so they just provide the answer. You know what's not going to happen on the exam? You're not going to have someone tell you the answer after a painfully awkward silence. Okay? So I know how easy it is to use good students as a crutch for being lazy in lecture. Let's talk about it, because I've done that before. Okay? So, I know how easy it is to know that, Prem will probably answer the question after Scott waits long enough, you know that there's going to be those people that you can depend on carrying over class time. And you know what doesn't work? It doesn't work when you're on an exam and you cannot be like, Prem, how did you do the second question? Okay. Does this make sense? Does everybody have their notebooks ready to go? Because at least I want to make this fair. You have access to reference things if you forgot. Yeah? Okay. So let's begin. Let's see, Tyler, what was chapter 3 about?
So we got notes. That was linear transformation.
Linear transformations. What else did we talk about in chapter 3?
Determinants. We have discussed determinants as well.
What about determinants?
How to do them.
Okay, what is the algorithm that we learned in the first section for computing determinants?
The algorithm
Yes.
of how to sector it off and break it down.
What was the vocabulary term we used for that?
I have a long definition you wrote down. How do I summarize this? Cofactorization.
Cofactor expansion. Everybody, you think this is funny until the laptop's in front of your face, so lock in, okay? Cofactor expansion. Do you know how to do cofactor expansion? And you can answer that for yourself. If the answer is no,
You're cooked.
fun fact, learn how to do it before Friday. Okay? Other things. Michael, what kind of special matrices do we care about when we're doing determinants that are faster than normal ones?
What kind of matrices? Isn't it upper triangle, lower triangle?
Yeah. Say it with conviction.
Upper triangle, lower
Did
triangle?
everybody hear Michael?
Mm-hmm.
Yeah, because that's correct. Why do we care
thank
about the
God.
triangle ones?
Because they make it super easy because you just do the main diagonal.
Did everybody hear that? What did we hear him say?
They make it super easy because you multiply the main diagonal.
Diagonal. Mr. Sam,
Oh no.
what's the rule that we learned in 3.3?
3.3. Kramer's rule.
What's Kramer's rule do?
Kramer's rule is let A be an invertible n by n matrix for any vector b in R of n. The unique solution of our x vector of A of x equals b has entries given by x sub I equals the determinant of A sub I b over the determinant of A.
What is the determinant of A sub I b? What does an A sub I b even mean?
A sub IB is the determinant of that column space? No.
No. How do you construct the A sub IB, Pran?
I believe we take that, we do the determinant with regards to that entry. So it would be like removing that row and column, and then do the determinant of the rest of the matrix.
Close. You're thinking of cofactor. What we do with that matrix A is I take my matrix A, and then it's all the coefficients, and I replace the column that's indexed with the B vector.
Right.
So that's what I mean by A sub I B. So if I'm taking the determinant of that, I need to construct it first. See how there's an order to this. Okay. Mr. Prem, what is 4.1 about?
It's the introduction to vector spaces, I believe. Oh, it was. Yeah, and subspaces. So we just define what it takes for something to be a vector space and the rules that would make something a subspace.
Okay. Do you know what the 3 axioms are that qualify something as a subspace?
It has the zero vector, it's closed over addition and scalar multiplication.
Did everybody hear Pran? Okay, proof it. What are the 3 axioms?
Includes the zero vector, its closed resolution, and multiplication of.
Okay, I'm convinced. So, if you're asked to prove that something is a subspace, you might have to know how to show those 3 things. Okay? A proof of showing something as a subspace constitutes taking those 3 axioms and then simply showing that it works. Denzel, do you remember the one little thing that's a detail that people might forget when proving something is a subspace?
No.
That's totally fair. Open up your notes.
Okay. Let me see.
What if the definition in subspace do we often forget? It's not one of the axioms. It comes in the preamble.
It's the subset.
Say that again.
Subset of the vector space.
Subset. So what happens if I try to make some sort of something a subspace, but it's not even composed of like the same elements as the original vector space? We just ignore that completely. You see how that works? So double check that. If you're asked to prove something, if it's a subspace or not, and it's not even a subset, then you can just move on. Okay, Mr. Agnell, what's 4.2 about?
Give me a sec. 4.2, no idea. I didn't put idea. Give me a sec. Identifying subsets. It's to identify what subsets are. Like different types of subsets.
Denzel, what did we do in 4.2 specifically?
That was the class I wasn't there. I don't have notes for it.
That is so tough. Okay, 1 second. 4.2, what did we do in 4.2, Rebecca?
It's the discussion of null spaces.
Okay, what is a null space?
It is the set of all solutions to A times the x vector equals the zero vector.
And Joshua, you obviously know what the vocabulary term is for the equation ax equals 0 vector, right?
In set notation?
We call that the homogeneous equation. Solution set to the homogeneous equation is going to be effectively your null space. Okay, what was the other space that was really common in 4.2?
Column space on
Column
matrix.
space. Yes, Andre, what is the column space?
The column space is an n by n matrix, A denoted by column A. It's a set of all linear combinations of the column A.
Okay. So then if it's a set of linear combinations, I might want to know what a linear combination is. What is a linear combination?
A linear combination. I don't know.
Gloria? Don't
There's
overthink it. What is a linear combination? What do you know that how we construct those?
there's some ways to express the vector.
Did everybody hear what Gloria said, or are you on YouTube and other things? Kyle, since you were listening very carefully to what Gloria was sharing for the class, what did she share?
I don't know.
Okay. So let me establish this real fast. We're reviewing. If I'm not in front of you, does that mean you start disrespecting your peers who are trying to share? No. Are we all taking the exam?
Yes.
Do we all need to be prepared?
Yes.
Okay, thank you. Kat, what did we talk about in 4.3?
Oh, 4.3. Wait. Linear equations.
At least, at a minimum, what's the section title, right? For 4.3.
I don't know where 4.3 went. I just have coordinate systems for 4.4.
So you have coordinate systems?
Yeah.
So what do you know about coordinate systems?
Find the basis.
The basis. Okay, everybody hear that? Basis? Yeah. Okay, find the definition in your notes if you don't have it yet. Do you have the definition of basis in there?
Suppose B equals a B
Say it with your chest.
vector. Suppose B equals a B vector to B vector n is a vector space for V and x vector. The coordinate of x vector is relative to the basis B.
Very good. What is a basis?
Basis is for what?
A basis for a subspace specifically.
I know that like colon space. The basis for colon space is the find the reduced echelon form and then to find the pivot colons and then it's the like match to the original matrix. I mean, yeah.
Very good. Miss Noel,
Yes.
what did you learn from 4.3?
About how to find the basis.
Well, is that what the section's about?
Yes.
So how do you find a basis?
You find a basis by finding the linearly independent columns of your matrix.
Okay. Why do we care that they're linearly independent, Jessica?
Let's see. Because it says so.
I mean, it's the way that that's actually kind of the correct answer.
Yeah.
Because what's the definition of basis include? There's two axioms.
There's B is a linearly independent set, and then the subspace spanned by B coincides with H.
Did everybody in the front hear what Jessica just said? What did Jessica just say? That was horrendous. Everybody, listen. Jessica's going to read it with her chest.
Let H be a subspace of a vector space V. An indexed set of vectors B equals the span, I think, of B1 to BP in V is a basis for H if properties or axioms 1, B is a linearly independent set, and the subspace spanned by B coincides with H.
Okay, so if you have a linearly dependent set, is that even candid for being a basis? No. Why not?
Because it goes against the rule.
Yeah, it's like definitionally that fails. Okay, so what do we do if I have a dependent set but want to make it a basis?
You need to reduce it so you can find your dependent columns.
Trim out the excess. Okay, trim out the vectors that are depending on the other ones. Make it independent. Okay. Well, span was mentioned in the definition of basis. I'm going to assume that means you know what the span is then, right?
Yeah.
What is the span?
Span, like from previous chapters?
Yeah, because it's an existing concept.
Yeah, so span is, what is it? How can I explain? Like, definition? I don't know definition.
I mean,
but yeah.
if I handed you a set of vectors right here, V1 through VP, boom. What's the span of those vectors?
Like coefficients, like group of coefficients in front of the, what is it, each?
Mm-hmm.
Yeah, vector, yeah.
What are those
and
coefficients allowed to be?
Allowed to be?
Mm-hmm. Are there any restrictions?
If it's independent, like dependent on other, what is it, independent, what is it, x3 or x4?
Well, say I have just a set of vectors, and I don't really care whether they're independent or not. If I just want the span of those vectors, what am I really collecting?
The all possible linear combinations.
Say it with your chest.
All possible linear combinations.
Did everybody hear what Axel just said?
Yes.
What's the span?
All possible linear combinations.
Oh, fantastic. Since you know that so well, you'll obviously know what base is, because a basis is just basically a spanning set. Mr. Prince.
Yes, sir.
when we were talking about null spaces, we were talking about column spaces. Then we combine, we have basis as a concept with null and column spaces. So if I want to find the basis for, say, the null space, what's the first thing I'm going to do, like, in the algorithm?
Do I simplify? Like,
Yeah. What am I row reducing?
You're gonna reduce like all of like the triangles, upper and lower.
Well, you definitely need to get, you need to row reduce, but how far do I need to row reduce for the null space? Aha, let me teach you a study thing right now. Our friend is stuck. That's okay. You want to know why? Because math is hard. But what that doesn't mean is you're okay with them just being stuck and then never studying that thing. Okay, so identify why you're stuck. If you can't answer a question, bingo, you now exactly know what to study for. You see how this works? Okay, that's why we study for these things, Mr. Emmanuel. So how far do we reduce? If I want to find the basis for a null space, how far do I have to go?
Reduced echelon form.
Reduced echelon form, beautiful. How is that different than the column space?
Okay, so it's rows and columns. So it's so.
Well, if I have to go all the way to reduced echelon
Yeah.
form for the null space,
Yeah.
and how far do I have to go for the basis for a column space? So study that one.
Okay.
Does anyone else know how far do you have to go?
Just echelon.
Just doesn't matter which echelon form. No. If you have a column space and you want a basis for it, you just need any echelon form. Yeah? Okay, if you didn't know that one, you have something to study. Mr. Lamide.
Yeah.
What did we cover in 4.5?
I don't have that note.
Do you have 4.4?
Yeah. Coordinates. Yeah, coordinate systems.
Did everybody hear what Alamide said?
Coordinates.
You have to say it a little bit louder.
Coordinate systems.
What is a coordinate system? Where does it come from?
Basis.
Yes. When I use a basis to look at a vector and then give it coordinates. So does that vector space need to be necessarily column vectors to start with?
Yeah.
Well, not necessarily. It works if you have column vectors. But the reason why we want coordinates is because if I have coordinate systems with a basis, I can start turning any vector space, polynomials, functions, other things, into column vectors. Yes? Okay. What is 5.5?
5.5?
I totally lied, didn't I? 4.5.
I don't know if I studied that for, but 4.5 is on the dimensions of a subspace.
Dimension. Ooh, everyone say dimension. Okay. What is the definition of dimension?
So the dimensions is the span, like the highest dimension linear combination of basis vectors for that subspace could like map onto.
Okay, I mean technically that does work.
Yeah.
What's the simple version of dimension? Yes. So if I have a basis and this basis contains exactly 7 vectors in it, what's the dimension of its corresponding subspace? 7. Okay. So, Lang, if you were asked to calculate the dimension of a vector space, what would you have to find?
Dimension of vector space. The number of the the number of vectors in the basis.
Yep, which involves finding the
way.
The basis in the first place, right?
Oh yeah.
So like say you're given a vector subspace, okay? And you're asked to find the dimension of it. Well, I'm not going to give you the basis for free, okay? So what does the crux of that problem turn into? Finding the basis and then making the observation from that, yeah? Cool. Dr. Hartnell. How's it going?
Pretty good.
Let's do 4.6. What did we talk about 4.6?
rank of a matrix.
And the rank, how do we define rank?
I don't know.
Looks like you found yourself a study topic. Boom. Okay. Everybody, what is the rank of a matrix? What's the rank?
Rank is if you have 3 independent rows. So if I have a matrix that's 5 by 5 and 2 of them are dependent and 3 are independent, the rank is 3.
Okay, so yes, but like definitionally, what do we mean? Just the definition of rank.
I'd have to look that up.
Okay, go for
What
it.
section is it?
4.6.
4.6. The rank of A is the dimension of col A.
Okay, everybody lock in. Did you hear what Kyle just said? Okay, say it again.
The rank of A is the dimension of col A.
Okay. What other math word is in there in that definition? Dimension. Ooh, okay, is dimension suddenly different now that it's being used in a different concept? No. Okay, what is the dimension?
The amount of linearly independent vectors.
Yeah, how many vectors are my bases? So if I want to find the rank, and rank is definitionally itself a dimension, is the procedure any different for finding a dimension? No. Okay, but it's specifically of which space?
Yeah, the column space.
Column space.
Yeah.
Okay. So if you're trying to find the rank, and we know that it is the dimension of the column space, then what is the procedure for actually accomplishing that practically?
Sorry, say that again?
Okay. So what is, if we know
Yes.
that rank is by definition a dimension of something, and we're told that it's the dimension specifically of the column space, then what is the realistic, just natural proceeding algorithm to calculate rank?
Oh yeah, you just have to find all the linearly independent column spaces.
Be more precise.
So you first have to, okay, one thing you could do, for example, is you could try doing row echelon or an echelon form as
Yep.
seen.
Did everyone hear echelon form?
Yeah.
Does it matter which echelon form? Why not?
Because you just want to find
Yeah, this is the column space,
Yes.
right? Okay, so we
Yeah.
have our basis for the column space, then what?
And then you find the amount of pivot columns, then you could use that to determine the number of, like the rank of the matrix.
Yeah, you just count them up, basically. Once you have that basis, count it up. It's that simple. Okay, Mr. Nathan. What did we cover after 4.6?
4.7?
That is the correct answer. Samuel. No. What was 4.7 about?
What? Change of basis matrices?
Change of basis. Ah, what did we have to do to change the basis? Algorithm. If I want to change basis, get a change of coordinate matrix going on. How does that work?
P to B to C.
Yes. What's the order? How is it handwritten?
So it's C on the C on the left and B on the right, but B is going into C.
Very good. Why does that specific order matter for the algorithm, Sam?
I guess that because it depends on a matrix multiplication that you're doing.
Well, yeah.
And that.
Because to solve for it, you need to know where you need to how to set them up. So because C is on the left side, you put C on the left side.
What do you mean by put C on the left side?
Because you need to find the inverse of, I think, the P. So
Not inverse? Chloe Winkler, you know which vectors we're talking about when we set up the change of coordinates matrix?
Wait, say that again.
So
What's
to
the
make a change of coordinates matrix,
Uh-huh.
which vectors am I putting on the left, which vectors am I putting on the right?
So on the left is the one that we're trying to go into.
Yes.
So we're trying to change the right into the left.
Bingo. Chloe and Chloe. You agree as Chloe? The
We are-
Chloes
we
have
are
come
one.
to
There is a
a
consensus.
consensus. The Chloe consensus. I'm gonna start doing that. Okay. Okay. I'm having fun. I'll do it again. All right. So what's
He didn't. I'll start here.
You definitely are not in this class.
No.
But I'm still going to ask you a question.
Okay.
Okay. What is 0 plus 0 plus 0?
3.
Okay, so when we switch over to the chapter 5, what's the new focus for chapter 5?
Chapter 5 is, let's see. That's eigenvalues.
Eigenvalues. Oh, okay, new section, new chapter. What goes with eigenvalues? What's the other thing that goes with that?
Eigenvectors?
Yes, both eigenvalues, eigenvectors.
Yes.
Okay, Michael.
That's me.
What is the definition of an eigenvector?
An eigenvector of an n by n matrix A is a non-zero vector x such that ax equals lambda x for some scalar lambda. A scalar lambda is called an eigenvalue of A if there is a non-trivial solution x of ax equals lambda x. Such an x is called an eigenvector corresponding to lambda.
Very good. Mr. Anderson, would you like to share with the class?
Sure. So we're explaining how to do the change of basis procedure. So you have your two bases, let's say C and B, and you want to go from B to C. You put C on the left from B to C.
Vectors of C on the left.
Yeah.
Right?
Yes.
You create your matrix, and so you have the vectors that make up the basis of C on the left, and then you do the augment, and then you have the vectors that make up the basis of B on the right. Then you reduce C to row-reduced echelon form, and this will turn B into your matrix P, such that you can multiply your B times B to get C.
Cool. So basically, that's what you do, irrespective of the example. Okay. Do you remember why we care about eigenvectors?
Eigenvectors, that's a good question.
Oh, so you could do A minus.
Study section.
Ooh.
Do you remember why we care about eigenvectors?
You can use it to create certain spaces.
Specifically the
eigenspace.
Eigenspace. What's an eigenspace?
It's the set of non-trivial solutions, or it's the null space of a non-invertible matrix.
Oh, did everybody hear what Prem just said? What did Prem just say? An eigenspace is?
It's a null space.
A null space. Ooh. Okay, we already know what a null space is, right? A null space is the solutions to your homogeneous equation. Okay? So does that mean when you do an eigenspace, it's a new concept? No. You just need to figure out how to get the A minus lambda I, and then you're just doing a null space problem all over again. Okay? Turns out. 5.2. What did we do in 5.2?
We started to learn the determinant of A minus lambda I equals 0 and how to implement that.
Okay, what was the name? What was the main vocabulary term we were introduced to?
Characteristic equation.
Characteristic equation. Agno, what does the characteristic equation give us?
What do you say?
Say it for yourself.
Eigenvalues.
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 Okay.
There you go.
Andre, it's not fun. It totally is 100% hilarious. I'm agreeing with you right now. Okay. How do I find my characteristic polynomial?
You set up across the diagonal that each value is subtracted by lambda, and then you take the determinant of the resulting matrix and set that equation equal to 0. And then usually you expand it and factor, and it turns into a polynomial.
Very nice. Did everyone hear what Rebecca just said? Okay, what other concept is involved in there for finding that characteristic equation? A determinant. Is that new? No. So then, tell me, what is the procedure for getting the eigenvalues corresponding to a specific eigenvector?
I don't know.
Study topic.
Next question.
I'm gonna have to ask the same exact question, unfortunately. What's our procedure? You can do this. think about the definitions, right? So if you know that the characteristic equation gives you eigenvalues, then if you're coming up with a procedure for finding the eigenvalues,
Use the characteristics equation.
Don't you need to just like do the a minus lambda I, and then you put when you combine them, you just do the determinant, and then you could either if it's like a 2 by 2, you just multiply it. But if it's not, you could pick whatever line is the best line.
yeah, so what you're describing is just taking the determinant, right?
Yeah.
Okay, cool. So the procedure for finding a characteristic polynomial is literally no different than just taking a determinant. So if you learn how to take a determinant, you know how to find eigenvalues, okay? Okay, what did we do in 5.3?
That's a hard word to pronounce.
I realized how mean that was, yeah.
Yeah. Yeah, so.
Andre.
Diagonalization.
Diagonalization, okay?
Okay.
What was the procedure?
So you have to find the eigenvalue first and find the linear independent linear independent eigenvectors of the matrix.
And then what do we do with that?
Find D is the diagonal.
Well, D being diagonal means what? What do we mean by a diagonal matrix, just by itself? Say it again, Rebecca.
Entries are on the diagonal.
Okay, so I'm allowed to have a non-zero entry off the diagonal?
Yes.
There are a couple examples in the textbook where they have it. I don't know the formal definition.
When we're dealing with diagonalization, which is specifically square matrices, though, what is my diagonal matrix composed of?
Zeros?
Zeros everywhere else.
Yeah.
Okay, so that's the key. Why do we care about having only zeros and only the diagonal has the non-zeros?
I don't know.
Study topic. Why do we care about the diagonal matrices?
Because determinate is on the entrance, like main diagonals, and then
Convenience, basically. Everyone get that? Diagonals are easy. And I know you guys like easy stuff. Okay? Did Agnel just say really?
Yeah. No.
Long time no see?
Sorry about that.
Okay. Tell me about oh, I wasn't referring to okay. How do I construct my P and my D once I've diagonalized the matrix?
Okay. The P is a matrix containing all the eigenvalues, and then D is the matrix. It's a diagonal matrix with the eigenvectors corresponding to the eigenvalues corresponding to the eigenvector of that P matrix.
You have it 100% perfect except for flip-flop.
Oh, okay.
So yes, it's the D that it's the diagonal matrix. It's just a single entry. So those are the eigenvalues, and then the vectors are the ones in P.
Hi.
Okay. So recap: what is the procedure for diagonalization?
So step 1, you find the eigenvalues of A, and you do that. Woo. Refer to previous sections for more. Step 2,
I like that.
find linearly independent eigenvectors of A. Go watch the video. He did an example. Final step, you have your P and your D, and then it's P times D, I think. And then you did a weird example of A to the 1 trillion, I think. Something like that.
That's actually an excellent summary. Okay, why do I care about diagonalization? What does that enable me to compute?
Basically, just that's the simple equation, like x1, x2, x3, like span.
Well, I mean, you could.
Yeah.
I'm thinking more like, say I wanted to raise a matrix to like a really high power. Why might I care about diagonalization?
To find the base.
Hmm?
No, I'm just kidding.
Okay, think about it. Everybody, visualize what a diagonal matrix even is. It's only entries on the diagonal. So if you raise it to any power, this corresponds to what? Yeah, raise the entries to the same exact power, okay? So it's a really, really efficient way to compute higher things. Study topic. Study topic.
Nice.
Mr. Prince.
Yes, sir.
Okay, so that's kind of like the overall topic. That's vocabulary, that's things. Now, actual problems. If I wanted to prove that something is a basis, how would I go about doing that?
So you find the basis. You get it determined? Oh no.
Well, let's think about it, right? I'm trying to prove that something is a basis for a subspace. It might help if I'm doing a proof to know what the definition of basis is, yes? Okay, study topic. What is the definition of basis again?
Oh no.
Okay. It's somewhere here, I swear. Oh, it's oh crap! I don't know where it went. Oh.
Study topic.
Also, yeah.
The further I move to the back does not mean the louder the talk in the front, okay? What's the definition of basis again?
Let H be a subspace of a vector space V, an index set of vectors B. B is a linearly independent set, and the subspace spanned by B coincides with H.
Bingo. Okay, so what are those two definitional axioms for a basis? What's the first one? Okay, linear independence, and then the second one is? Yeah, span needs to coincide with what? The actual subspace. Okay, so if I'm trying to prove that something is a basis for something, and if I never at some point demonstrate that there's linear independence, is that even a valid proof? No. Okay, does that require like black magic to conjure up the concept of showing something is linearly independent? No. You do it because it's in the definition. Okay? Outline the overall pseudocode essentially for a proof to prove something is a basis for a subspace.
Okay, so the first thing you do is row echelon reduction, and if it has a pivot in every single column, then it means it's a linearly independent set of vectors. And if it's linearly independent, then you can prove that by showing that every single vector in the subspace can be spanned by that linearly independent set because it is in the E1, E to En form, because by definition, every single vector could be reached from that one form.
Bingo.
So yeah.
Everyone catch that? Say it with your chest.
Row reduce the matrix to the row echelon form, and if it has a pivot in every single column, then it's a linearly independent basis set.
Yes. You hear the row reduction part of that? So if you're not able to just by inspection, you still have the tool of row reduction. Is it technically possible for there to be situations where there is a shortcuttable method for independence and dependence? Sure. You're nodding your head, Chloe.
Yeah.
With your chest.
Yes.
Share.
Okay.
How?
Like if the vectors are multiples of each other.
Bingo. Everyone hear that? Multiples of each other. So if I have vectors v1 and v2, and I can show that v2 is just a scalar multiple of v1, are those dependent or independent?
It's dependent.
Dependent. So does that work for a basis? No. Okay. If I wanted to prove that the column space is a subspace, what three axioms do I need to show?
I have no idea, honestly.
Study topic. We can back it up to what the axioms are for a subspace in the first place.
Axioms for subspace.
study topic. Mr. Colby,
What was the question?
if I want to prove that the column space is a subspace, I might want to know what the axioms for a subspace even are, right?
Perchance.
What are those?
Study section.
You know, that's entirely valid. Mr. Kyle?
What are the axioms for a subspace?
Isn't it like zero addition and scalar multiplication?
Okay, be more specific on what you mean by all three of those.
Zero vector is in
Where
it.
would this be in my notes?
It contains zero vector.
Okay.
It's closed over addition, and it's closed under scalar multiplication.
Yeah.
There we go.
Addition, subtraction.
Okay, we've run around this term closed under. What on earth does that even mean, though?
So, is it fine if I visualize it?
Yeah, that's fine.
Okay, so closed under addition, for example, if we take any two linearly, okay, they are linearly independent. If we take any of those two vectors, for example, and you add them together, it also still lies within that, it's still within that vector space. If you subtract, it's still within that vector space. If you multiply by a scalar, it's still within that vector space.
Good. Everyone hear what Victor is saying? Or sorry, not
Christian.
Victor means. Christian.
Yes.
Yes?
Yes.
Okay. What is closure of, how do I show that something is closed under addition? Like analytically.
You just need to show that when you add the two things together, the resulting product is still in the space.
Exactly. That if I perform the operation on two objects that are in the space, that if their sum is still actually in the space, that's all we mean by closure. Okay? Okay.
It's me.
Is the span of a vector, is the span of a set of vectors a subspace of that set of vectors?
Yes, if it follows the three axioms.
Which are?
The zero vector, the closed under addition, and scalar multiplication.
The Chloes can answer corporately.
Okay.
Everyone's like, that's not fair. Well, tell your mother they should have named you Chloe.
That's true.
Okay. Don't actually do that. I'm recording this. It's crazy.
Unlisted YouTube video.
You will get seasick watching this. All the people who didn't show up in class are
Why are you making it worse?
What is the outline to prove that the null space is a subspace?
Oh,
Oh, find the general solution for A, the vector of x equals 0 in terms of the free variables. Row reduce the augmented matrix to reduced echelon form to express the basic variables in terms of the free variables. Decompose the solution vector x, giving the general solution into a linear combination of vectors where the weights are the free variables. The resulting set of vectors in linear combination form a spanning set of null A.
Okay, so that's to span null A.
Can
But
you say
what
the
about-
question again?
Yes, if I want to prove that the null space itself is a subspace, what do I need to show?
Do we just need to show the
you need to do
same
the
three
three
axioms?
Yes.
Okay.
Which are?
That it
there's
contains a
zeros.
zero vector, closed
They're
under
closed under
vector
addition
addition, and
closed
scalar
under
multiplication.
Very good. They even answered in unison. Are they the same person? Is their next conspiracy theory?
One brings up.
Okay. I feel like this is fairly indicative for myself to see exactly how prepared people are. And lock in, okay? There's about half of the subjects that we've all decided to kind of corporately forget, which is really not great, considering roughly 90% of the sections that we've covered are on the exam. So, but do those main things make sense? Do you see how I don't need to show you an example of proving something is a subspace? Because you already know. If you know the definition of what a subspace is, if you know the definition of the object that you're trying to prove, follow the list. Put it in the definitions, go through the steps. You know how this stuff works. Okay? Now, do we say, I recognize the definition. Sounds like I'm ready for exam day. Is that what we want to do? No. Okay. Is it enough to be like, I completed like half of the homework? Yeah, I should be fine. Is that enough? No. Is it to say, wow, it's almost like it has been repeated over and over and over and over again to the point where I basically stopped hearing it to read the book, to look for helpful study examples, and to review the definitions? Do we just ignore that? No. So do you think I'm going to care throwing a massive 0 out of 20 on a problem that was so easily solvable if you just opened the textbook to read the definition? Yeah, I'm not going to feel bad whatsoever, okay? So.
Yeah. Remember to draw some funny pictures.
What would you say the ratio of computation to like writing being either proofs or definitions is?
That's actually a really fair question, and I'll answer that one. It's going to be, you need to, since Chapter 4 is so heavily conceptual, you're going to have to show a lot of things. They're relating to all of the primary definitions. Pretty much every single thing that I have asked every single one of you is something that you're just going to have to need to know, actually. Okay? So, do you see how it's hard to answer? Because every concept itself comes with algorithms, right? By knowing what the definition is, that just implies that there's a procedure that goes along with it. So know every concept well enough that you can set up every procedure for every concept. So that way you don't have to be stressing, am I just going to have to know it, or will I have to use it? Okay? Yeah.
So if we have a diagonalization problem on the test, would it be a 2x2 matrix or a 3x3? So I'm not manage my time. It takes a while.
I'll put it this way. I believe in fair testing. I don't believe in obnoxious testing. So you're not going to have a question that will take just naturally 30 minutes to get through, because that's just not fair. Okay? You're going to still need to know the concept well enough, and you're not going to finish the problem if you're not familiar with the concept. But you don't have to worry about, oh my goodness, do I need to prepare answer with where the answer is going to be 2713 divided by 17 to the square root of, no, okay? So it's not going to be intentionally torturous to solve. You just need to be familiar enough with the concepts that you're not just recognizing them, but that you're fast enough to then recognize to do. The main weakness I found with the first exam was you all were really good at just recognizing the concepts. Fun fact, recognizing concepts and then trying to refigure out how to solve the problem is you're just not going to have time for that on a 55-minute exam, okay? There are 5 questions. You need to use all of those minutes wisely. So the trick is not, any individual question is actually not hard. What's hard is you're only going on recognition, and you're not going for understanding so that you can replicate fast enough.
So there's no bonus question?
Yeah, of course there's a bonus question.
Oh.
Yeah. So go know your stuff well enough that you're not trusting on pure recognition, because if you're going on pure recognition, you will simply run out of time, and your grade still plummets anyway, okay? So don't do that. It's not enough to just be able to recognize everything. You have to be familiar to the point where you can point and shoot and write and go, okay? Any other questions?
I'm still a little bit confused at how you answered Jessica's question. So, are you saying that we should know the definitions to do calculations, or are you saying that there still will be proofs?
I'm saying that it's impossible to solve a linear question involving jargon if you don't know the definition. So you don't have to handwrite any more definitions by rote.
Okay.
Okay, that was just kind of like, hey, welcome to 300 level math.
So it's going to be calculations, but you need to know the definitions in order to solve them.
Yeah, there will be calculations, proofs, the whole mixture. And there's no way to do those calculations or proofs if you don't know the definitions, okay? You don't need to just memory rote the definitions, but if you don't know them, good luck on literally any of the questions, basically, okay? Cool. Well, I will continue to pray for you all. Show up. Are we doing, Dr. Harder, are we doing another early, they can come at 1 o'clock?
Yeah, let's do that.
Okay, so you can come get an extra 15 minutes.
Yeah.
Show up at 1.
Start the test at 1, so you'll have an extra, 15 minutes.
Cool, awesome. All right, you guys are awesome.